Hey, welcome back. Today we're going to be talking about alpha, beta, and gamma radiation penetration power. What does that even mean? And what ionizing radiation is, and how that all relates to the magnetic field of the Earth. So we're mainly talking about ionizing radiation. What does ionizing radiation mean? This is primarily for chemistry students or physical science students who need to know something about this. So first of all, there are alpha particles that you can see over here. These are like helium nuclei, and I will put a link in the upper right about now if you want more intro into alpha particles. But they are given off by unstable nuclei of atoms. So the unstable nucleus of each atom can sometimes give off an alpha particle or alpha radiation. Similarly, an atom can give off a beta particle. In this flavor of beta radiation, this is a high energy electron that's been given off, and notice that both of them can penetrate different levels of material. So for instance, the alpha particle will get stopped by just a piece of paper. Remember, this is a helium nucleus essentially here. And the beta particle can actually go through paper but will be stopped by a very thin layer of like aluminum or some other metal. And lastly over here we have gamma radiation. Gamma radiation is just effectively a very high energy photon. And that high energy photon, so packet of light, can pass through a lot of things like paper, aluminum, human skin, human tissue as well, which is where it gets dangerous. It can pass right through our bodies and cause problems, cause ionization. So that's what we're talking about today. Notice that gamma radiation can even pass through lead, which is just crazy. Alright, so what is ionizing radiation? Well, let's take a look. So ionizing radiation, if you have something like a gamma ray particle or something that has a high energy because it has a high frequency, when it comes in and hits an atom, it can cause an electron to be knocked off of that atom. Think about playing pool. It's similar here, and there are conservation of momentum ideas going on, as well as conservation of energy ideas going on. But high energy photon, this gamma ray comes in, knocks an electron off. Now you might think, oh, what's the big deal? An atom loses an electron. Well, the big deal is if that is involved with your DNA, or my DNA, or someone's DNA that we obviously care about, what happens is that can cause chemical reactions to occur. Like let's say you have an electron being knocked off or ionized right here, or right here, or right here, or maybe even on these parts of these atoms right here. That can cause cascading negative effects where you can actually get mutations start to happen in DNA as a result of ionizing radiation, of high energy waves coming in from the sun or a star. That would just cause massive problems. So one way to think about this is to think there is, as far as we know, no life on Mars. But one of the real challenges that life on Mars would face is because Mars doesn't have a magnetic field on it, at least not a significant one like the Earth does because of its iron core. Then these harmful rays are going to be coming in, gamma rays from the sun, solar winds, comes in and causes ionization to happen, kicks off electrons off of atoms. If it does so in really important atoms, then what happens is the atoms can have mutations if you're talking about atoms involved in life. Alright, and so a lot is going on in this graphic, but this is really helpful in understanding what's going on in this situation. So first I want to draw attention to this statement over here. Low frequency waves, I could draw that with something like a longer wavelength. The wavelength is just the distance. This is one wavelength right here, the distance between one crest and the next crest. So if you have a low frequency wave on this end of the electromagnetic spectrum, that's what you could say this whole thing is. The left side is the low frequency side. That also means the low energy side of things because the energy of each wave is related to the frequency of the wave. So notice that this has a lower frequency on the left side. If we're talking about something like gamma rays, these would be waves with a very high frequency or a small wavelength. Okay, so looking at the left side, notice that this is going to be low energy. Alright, so notice that as you go up, this is non-ionizing. In other words, generally these photons, these packets of light that come in, or alpha radiation or beta radiation, that kind of thing, don't have enough energy to be ionizing, but if you get above a certain level, that includes microwaves as well, by the way. Generally, microwaves don't have enough energy to be able to kick off electrons completely and cause mutations and things. They just vibrate the atoms more quickly, especially water molecules. But we get to an important break right here where on the right side of this, we have an ionizing type of radiation. This has enough energy to be able to kick an electron off of the atom itself. So if you have a high energy wave come in like this, it can meet an electron that's a valence electron around the nucleus of an atom. And what it can do is kick an electron off of the surface, and that's really dangerous if it is especially DNA of a creature, because then that can have a cascading effect and cause mutations. And that's fundamentally the problem that we're going to see right here. We can get damage to DNA, we can get broken bonds here. If you take a look down here, these are useful as well to get an idea of what we're talking about for these things. And notice that you can get electrons be excited. That means they get bounced up to higher energetic states, to higher orbitals, but then they fall back down and give off another photon. I'm talking about this right here. Here, this is really important. We're going to have photosynthesis happen with some of these visible lights frequencies, where again you have, instead of the electron being totally kicked off of the surface, chlorophyll molecule, let's say, can absorb that energy. Sometimes that energy is captured. In other words, there's a chemical reaction that can happen right here at this point with an excited electron, and if that's the case, you have solar energy converting into chemical energy, which on a very foundational level is what happens with photosynthesis and allows life to exist on our planet. And so lastly, I just want to conclude, is a magnetic field for a planet necessary for life? It turns out that the answer is almost certainly yes. We think so. If you have harmful rays from the sun coming in, the nice thing about the Earth, one of the many, many awesome things about our amazing home planet, is that it has a molten iron core in the center, in the outer core of the Earth. And so as a result, that acts like a giant magnet. And that has good effects because it's able to reflect a lot of the harmful rays from the sun. These high energy waves, not all of them, but a lot of them get reflected off. And as a result, life can flourish if we allow it to on the Earth. Hopefully that's been helpful. If you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.